Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 478, minimum operations to equalize subarrays. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. This one I'm not going to go into super detail because this is a very long problem to do that on. There's a lot of components. I'm going to go over some of all these components, but I'm going to leave it up to you to do the homework to kind of explore what they mean, right? Okay, so first of all, this is the constraints are big-ish. You can just do brute force, obviously, if you can, and this is not that interesting of a problem. Let me bring up the drawing board real quick. So the first idea that we're going to do is this idea of k, right? Like increasing and decreasing by k. And this part is pretty simple, right? Because basically, if you mod every number by k, if the mod result is different in a subarray, then it is not possible. In English, if k, let's just say k is 2 as an example, right? If you have odd numbers and you want to add or subtract by 2, you can never get to an even number. That's basically the same idea, but for different k, so more than just k is equal to 2. But with odds and evens, it should be easy to visualize, right? Okay, so that's step one. Step two is that for a given range, let's say you can do it, right? Because if you can do it, that's trivial and easy. We'll talk about how you can do that later in terms of code. But if you can't do it, then what can you do? Well, now it is just about, well, what number do you convert it to get the optimal result, right? And turns out in this case, it is the median. Why? We just have a bunch of numbers and it doesn't matter what they are. And let's just say k is equal to 1, so every number fits, right? Maybe even big numbers, it doesn't matter. The idea is that you move it to the median. And if you have two medians, either one is fine. You may want to pick one just because, just for consistency, right? But yeah. Okay. So why do you want to do the median? The reason is that because, let's just say, like I said, let's say k is equal to 1, and that means that everything to the left side of this, smaller numbers, well, you gotta do +1 for every delta, right? And that's the idea, right? So that means that, and everything to the right also -1 for every number, right? And what do I mean by that? That means that, well, because of 7, let's say we move, and this is a little bit weird because I have two medians, but let's say we change. Let's say we don't move at 7, we don't meet at 7, we meet at 6 instead. Then what does that mean? Well, that means that all the numbers to the left is 1 closer, right? And because all the numbers to the left is 1 closer, that means that we save, if you will, 2 points or 2 score, whatever, right? But because now there are 4 numbers, including the 7, that had increased cost, that's a +4. So you have a -2 +4, that means that this is, well, a net +2, which is not optimal. On the other hand, if you move from 7 to 8, well, on the left side, this is going to be -3. Oh, no, sorry. If you move from 7 to 8, on the left side, it's going to be +3 because it got farther away from 3 numbers. But it gets closer to 3 numbers, so it's going to be -3, which is going to be net 0, right? So it's net 0, meaning that it doesn't change. And of course, if you do it the same thing from 8 to 9, this is the same thing, right? 3 numbers got closer, 3 numbers got farther away, so it's net 0. So that's basically kind of, the visual proof, if you will, of trying to get the median, right? So okay, so now you have 2 components, at least, right? You have to try to figure out if they're even. The way that again, let's just try odds and even as a number, right? So here maybe you have like here maybe, you mod everything by k and you have 0, 1, some sequence, right? And of course you do have to generalize it beyond the 0 and 1s. This is just for visualization. Is that, okay, given a range, and there are actually a couple of ways to do this, now that I think about it a little bit. But yeah, there's actually a lot of ways to do it. But the way that I did it is that, okay, given a range, well, what is the min number, right? Well, if this min number is 0 and then the max is 1, well, if they're all equal, then the max should be equal to the min. Straightforward. Yeah, so that's basically the idea behind this problem. What I did, right, is that, okay, so now I know that I need a range minimum data structure, which there are a couple of those you can use. You can use, and I don't know if it's fast enough, but you can use them. There's binary index tree, there's segment tree. There are a lot of different things that people have used. I use RMQ, right? Range minimum query and range max query. For, well, pretty, because that's basically what you do with these queries, right? Okay, so basically that's how I figure out whether a range is, quote unquote, good, right? Good to solve. Okay, so now we filter out the queries that are bad because, you know, they're bad to solve, right? Then now there is a couple of things that you this is a hard problem, not gonna lie. So how do I explain this? Okay, well, first of all, now the two things, you know, you have queries that are good. The first thing is saying that, okay, well, let's say, well, now we know that given a range, as we're trying to figure out, given a range, we're trying to figure out let me try again. Given a range, we're trying to figure out the median, right? And there are a couple of ways you can do this. The way that I did it is I actually just created 2 queues or 2 priority queues, 2 heaps, and just maintain the median, right? And this part, I'm not going to go into super detail, but and I actually lied a little bit. I used 2 sorted lists, but you can imagine having 2 heaps, 1 min heap, 1 max heap, meaning that the top of the this is max, this is min, and then basically when you put in a number, you just figure out which one to go in, and then, you know, and then you keep the size relatively similar or the same. That way, then you know where the median is, right? Because, you know, and every operation is log n because you only do one you insert it once, and then maybe remove it once, and then add it another time. So maybe 2 insertions and then remove or something like that, right? For each real insertion. Okay, so then now you have 2 heaps, and then you have the median, and then now what? I'm not going to go over this because the median part, just because it is a key part to a lot of easier problems. There are Leetcode problems like that, so you should work on it, right? Okay, so let's say now you have the median. Well, how do you get how many moves you have to do? And this is where actually, because you can actually find the median in an easier way, right? Meaning that you can use like a binary search tree or something like that, and you can find the median on a binary search tree just by maintaining it. But the key part for me anyway, and actually you could still do this with binary search tree, I suppose. But I didn't do it that way. Though now I think about it, maybe that is an interesting way to do it. But though you would have to have a binary search tree that does rebalancing and still keep tracks of the sum and stuff like that. Not a trivial thing, but possible, right? But this way is easier for me, which is that I just have 2 halves with heaps, right? So okay, so given a median, the way that I think about this is actually very visual. The way I think about it is that, okay, you have, you know, let's say you have 1, 3, 7, 10, 29, I don't know. So then now I think about it as a graph, right? Or a bar graph, if you will. And you have like 1, maybe 3. They're not drawing the scale because I don't have enough room for 29, but you get the idea, right? So then, you know, right? And then we know what the median is. So then the visualization here is that there are 2 parts to the you know, compared to the median, right? There's the, let me change the color real quick. There's the left part and then there's the right part. On the left part, well, you know that you have 2 numbers, or you could keep track that there are 2 numbers, and you know that you're trying to get to 7. So that means that this area is just 2 times 7, right? Because this is length 2, this is length 7 to keep track of the median, and that, this is going to be 14, right? But, and maybe I shouldn't have drawn the space, but either way, but you know that you have 1 and you have 3, so then that means that this gap, it's just we keep track of the sum. So because we know that this is 4, 1 plus 3 is 4, we know that here we need to fill out 6 and just fill out to, I don't know, whatever, 4, right? So that means that we need to add 10. So that's basically the idea, right? It's very geometric, it's very visual, right? So so if we keep track of the sum of the left side, we could do some maths to get how many moves we need to get to the median, and the same thing to the right, right? We know that we need to get to here. We also know what the sum is, which is, again, maybe I shouldn't draw the space, but something like this, right? So that means that we just try to figure out, this thing would be, would give you the answer that you need. And that's basically it. I mean, of course, you have to also factor in K a little bit just to, because it's not one move at a time, but that part is also relatively, honestly, pretty trivial. Oh, I forgot one part. So that's basically the idea once you get the median, right? But that's not it. Because I kind of skipped over the probably one of the more important parts, which is, well, how do you answer the queries? You can't really, construct them one by one. Like what we said here with, I don't know why I put the things away. I guess I thought I was done. But you construct the left half and the right half for the rolling median, and it's fine. But how do you construct the rolling median? And this is something called we use this idea, and this is an advanced idea. It's only something that I've done probably 2 times in my life, but I don't do as much competitive programming anymore. You gotta remember that. In my days, it just didn't come up. But the idea here is called an idea called Mohs algorithm, and it's an idea that is based off square root decomposition. I'm not going to go over square root decomposition too much, but I am going to do a quick proof of the Mohs algorithm and how it applies here, right? So the idea here is that, okay, let's say you have an array, right? And I'm going to illustrate an array like this as a thing. And then now you try to break them up into square root of n blocks. Why? Well, we'll go over it in a bit. Let's just say there may be, okay, let's just say there are a lot, whatever, there's square root of n. Whatever, right? So there, n size, each block is going to be square root of n size, and of course there are square root n of them, right? Because the square root of each one is size square root of n. There's square root n of them, so total is n, right? Because it's square root of n squared, right? Okay. So that's kind of the core idea. And for Mohs algorithm for this query, you can think about these as segments, right? Each query is a segment, and they could go like any which way, right? The idea here with Mohs algorithm, which is the proof is kind of beautiful, if you ask me. It's very like fun and interesting. Is that, okay, well, what if we sort the queries but by block, right? And there are, like, you can make this more complex for sure, but even the non-complex version is enough. So what you want to do is you want to sort the left endpoint by blocks, and then on the right endpoint just use it as a tiebreaker. It doesn't really matter. Don't. But what does that mean? That means that we'll have to kind of delete this thing here. Okay. Well, why do I do it this way? Why does Mohs algorithm do it this way? The reason is because then now, and it doesn't really, I guess in this case, I'm just kind of pretending everything is in the same block, right? And in this case, the right endpoint is sorted even though they're in the same block, right? Then now the idea is that the idea here is that, okay, now everything on here, right, on the left endpoint, well, what happens? What happens is that at each endpoint it goes well, here it goes to the right, actually, and then it goes to the right again, and then it goes to the left, and then it goes to the right, right? But for each query, we know that it is within the same block. And the same block is, again, size square root of n. So that means that the left endpoint will move at most square root of n times, right? For each query. Right? So, and then the right endpoint, well, the right endpoint is actually sorted, right? That means that in total, for each, in total, this is just going to be O of n, right? And in the worst case, right? What do I mean by that? Well, this is O of n over all queries in the same block, right? And so that means that for each block, it will take O of n number of, or the right endpoint will move at most O of n moves, right? Because, yeah, like, in the worst case, maybe you start off here and then it just goes all the way to the right. But here, it never moves back for the purpose of this one block. It's not quite precise, but, right? Because, well, why? Because we sorted by it, so that's why it won't go back. And because this is O of n for the entire block, well, how many blocks are there? There are square root of n number of blocks. And as a result, that means that on the right endpoint, in total, it's going to move n times square root of n. And on the left endpoint, well, there are n queries, so yeah, so it's going to be q times square root of n or something. But yeah, that's basically it. And the idea behind that is that now everything is bound by n times square root of n. And that's it. There are some optimizations that you can do. For example, the way that I wrote my code anyway is that when I start a new block, I'll write a new one. When I start a new block, say we move it to here, right? I still sort it this way, so then now it goes from here to all the way to here, which kind of adds some time to it, so you have to be, which is not great. There are some idea about sorting the right endpoints so that on the second block, you might, well, reverse the order, right? Because if you reverse the order, then now it looks more like something like this, because it's now the order is reversed. So then now you can just go incrementally smaller, and it'll be faster. But those are all constants, right? Good constants, by the way, but still constants. And that's kind of the entire idea behind this problem. It's already 20 minutes in, and I didn't even go over super detail, and that's why. But yeah, we'll just go over the code now. We have the RMQ, as I said. You can replace this with binary index tree or binary index tree or segment tree or anything like that. And then I have the rolling median. We'll go over that in a second, but I'll go over the core part of the code first, which should actually look pretty straightforward. If you have a good understanding, right? Oh. Huh? Oh, this is my Python code. That's why. Wait a second, hang on. No, I guess not. The reason is because my Python code maybe needs some optimization. I converted to Java and it's correct, but the ideas is what's focused. I was running some stress tests. That's why there was some extra code that wasn't in the final version. But yeah, make it bigger. Okay, so we have N, we have Q. This is the X mod K thing we talked about. This is the odd even thing. This is just so that we can see if it's possible, right? And here we both create a min and a max. And then for each query, we want to filter them out. If this is not possible, we set it to -1. Otherwise, we put it in this thing. And again, this is going to be sorted by the block, right? Oh, did I mess this up? Huh. Maybe that's why it's too slow. This should be this. Huh. I am curious now. I mean, it may still be too slow, but that's a bad typo. Huh. We'll see. So maybe I have no one to blame but myself. Okay, still too slow by 1 input. Did you see that? Oh, it doesn't. I don't know why. I don't know where it shows up. But what the? I don't know what Leetcode is doing. Okay, fine. Either way, it was timing out by 1 input, so I don't know. Whatever. I mean, it's ACs anyway. But my point is that okay, but also just to show you the power of most algorithm, right? Because if I did it this way without, this is the equivalent as just bring L, because you times every number by B, it still sorts the same thing. So this is basically just sorting it by the segment, which doesn't do much, which actually still was pretty fast. But once you kind of convert it to this is the key part of most algorithm, is converted to the block. You want to sort by the block, and then you tie break by the right endpoint, right? Maybe we'll play around with this, or we'll do it afterwards, right? To kind of do the looping back thing, right? Okay, so then now we do that, we sort. This is just a starting thing, and we keep track of the rolling median. I'll go over this code also later, but this is basically what we said, right? So now we keep track of the left endpoint. We go either left and right, depending on if it's left of the L, the query L, and right on the query L. We add it and we add it and we move it to the window, the range that we care about. Same thing for the right side, and then at the end we just get, again, one median is something that I wrote for this problem on the spot. You can watch it during the live portion. So we'll go over it for sure. Otherwise, and then that's it. We have this thing that gives us a number of steps away. We do it by K, and then that's our answer. So let's do the one median first. So all this is code I wrote during the contest, so you can watch it during the live portion in case you're wondering. And yes, I did put comments on my code so that I can make sure I get it right. But this is the variant that I keep track of. We have the left side and the left sum, right side and the right sum. Rebalance we'll talk about later, but we want to either add to the left side or the right side, right? Doesn't really matter as long as the invariant is true. And maybe one that I didn't mention, but maybe should be obvious, is that self.left max element is smaller or equal to self.right min element, right? So you have the left side, you have the I call it the left and the right side, maybe you could call it min on the max, I don't know, right? But yeah, so you add it to either the left or to the right, and then we rebalance. We move this, well, we just check whether it is on the left or the right, and then we rebalance, keeping in mind that we also keep track of the sum on the left right side. And then rebalance is just, if there are too many things on the right side, we move the smallest number and put it on the left, keep track of the sums as well. If there's too many things on the left side, we do the same thing, just we move from the left, put it on the right. And then the delta, for the delta, we get the median, which we define as this. Keep in mind that if there are two medians, it doesn't matter which one you pick, so just be consistent and make sure that it always works. The left delta is what we said. We have the median, so we count it by the length and minus the sum. For the right side is the sum minus the length of the thing, and then just return it. And that's it. That's all I have for this one, I think. So this I had it pre-written, so I don't know, it is fine. This one I wrote, you can take a look here. Maybe I'll make it slightly smaller for a second so you can see everything in case you're wondering. Rebalance, add and remove, and delta, right? Let me also just give you a glimpse of the RMQ min, but this is pretty standard stuff. And and then yeah, Mohs algorithm. Mohs algorithm is pretty straightforward to write. It is just the power is in the complexity, right? Because yeah, that's crazy actually. That I didn't notice this. Or I miswrite it, right? So the one optimization that I was going to write, and it kind of, I don't know why Leetcode is so weird, but it came up and then it popped away. But if I had done this, it went like 1,000 out of 1,200 or something like that. With this, it basically solved every input except for the last one. So we'll do one more optimization, right? Which is that if it is equal to 0, then we do it this way. Else, we'll do a negative R. So then we kind of sort by the other way. And yeah, see if that gives us a better thing. Oh, it gives us an AC anyway. I guess that's the better thing. It may not be fast enough because Leetcode is weird, but oh, there you go. So maybe that's all I needed. But yeah. So as you can see, these optimizations do, at least for Leetcode, it matters. But I don't know how I feel about it. But yeah, and just to be clear, this is the thing that we were saying about going left and right, so that doesn't jump all the way to the left and then go back, and just a lot fewer operations. But yeah, that's it. That's all I have for this one. Let me know what you think. Thanks for watching. Yeah. Oh, I didn't go over the complexity. I mean, this is linear-ish. And log n-ish. I mean, it's not the dominating thing. That's why I'm not looking into it. But yeah, for each query, well, this is for each query. I mean, this is just n square times square root of n, as we said, because plus q times square root of n. Because this is just Mohs algorithm, and we already kind of did the proof on the complexity, so it's hard to kind of see from code, honestly. But yeah, that's it. That's all I have for this one. Let me know what you think. Thanks for watching, and yeah, you can watch me solve it live in the contest now. I thought that it actually didn't matter which direction you go, but actually maybe I just didn't think about it carefully enough, which could have been an easy wrong answer, to be honest, but it just didn't pass the examples, which is lucky. Okay. How am I doing on time? Minute 22, an hour 22. People are very fast. 1 minute on Q4. That seems crazy. Alright, you're giving a number K and exactly K. Alright. So K is constant. And K could be big, so no K shenanigans. K is not that big. With these problems, one thing that I always try to do is see if we can process the queries instead. Maybe we can, I don't know. I mean, the K part is easy, it's just the mod, right? So then it's just about, how do you calculate that? Well, you calculate it by, so it's the sum. So, okay, so the median value is what you want, right? Probably. Is it the median or the average? I guess average, actually. I mean, median works, but actually, does it? No, it's the median, right? So then now, no, it's definitely the median, right? So how do you get a median of a range? I don't remember anymore. Because once you get the median, then it is just a sum. and the sum is easy, right? So how do you get a median of a range? Can we pre-process? That could be tricky. I don't know how to do it anyway. Is there a median seg tree? I mean, I guess the median is the hard part, right? Is it median? I'm pretty sure it's median. No, it's the median. Yeah. Okay, I mean, first we do a binary index tree on the min and the max of a range over mod, so that if not every number is the same, okay, that's easy. Median, how do you find a range median query? Can I do square root decomposition? What is the complexity here? Was it 40,000? Is that what? 40,000 is 200. So n square root of n, 40,000. Let me just put a code in the calculator. 8 million. I guess it is square root decomp then, right? Probably. Annoying, but okay, fine. Is that true? But then you still have to do a log thing for each query. Square root of n times log n times q is going to be too slow, right? pre-process these? Can I do some sort of sliding window? What is the? I'm thinking of like that walk thing. Square root decomp walk. What am I thinking of? What is it called? What am I thinking of? I think I got it, but I forgot what it is. Oh, excuse me. Don't have my water. Okay. Because I'm thinking of, you know, how the segments do, right? So that is literally just what is it called? Screw decomposition. It's like a special one. Mohs algorithm. It is Mohs, isn't it? Okay. I mean, I guess that's it, right? I guess that's why people got it so quickly. Maybe. I don't know. I'm not gonna get it that quickly. It's been a while. We'll learn together. I think I did it like a couple months ago, but I've only done it like maybe twice in my life, to be frank. So I'm not like it's been a while. Okay. Let's give it a try. How much time do we have left? We have an hour 12. Yeah, that sounds reasonable. Let's give it a try. I might be wrong, honestly, but it's fine. So we use Mohs for median, maybe? Yeah, that should be okay. Maybe not. I don't know. Maybe it's still too slow. But first, let's do a. Where's my? I'm trying to find my thing, but trying to find my code, but okay, fine, I can't find it. Because my server is down. I guess I haven't checked it up. Yeah, I guess I don't need it. I guess I could use RMQ, right? Yeah, good enough. probably could roll them in the same thing really, but what we want, right? Let's go reload. Right, okay, so we have it for min and max, and then now yeah, so then in theory we pre-process these, right? So okay. Oops. Right, and then now for XY, whatever, left, right, in the queries. Then now what we want is if right, okay, else then we can't just put it somewhere, right? So left, right, and index. What do we sort by again on most? We sort by the block. Now, okay, yeah, you have to do a block thing. That's right. It's slowly coming back to me. Maybe. Yeah, maybe I could put this in here actually. Okay, so. This is gonna be slow because I don't remember that much, but okay, so block as you go, just go B as you go to N, square root of N, right? So then now it is gonna be, yeah, we just sorted by L, right? Okay, well, yes, but actually we do want to maintain it. So this is the sort. Say, we could probably clean it up, but that's maybe okay. Should we just return this anyway? They should at least give me a 1 negative 1. Yes, we do have a negative 1 in our midst. These should not be erased though. I think they're just nuns. I don't know why they convert them to arrays, but okay, fine. Okay, and then now, okay, oops. We don't care about these technically. Now that they're sorted. Let's go left, something like that, right? And then now we go while left is greater than left, then we go smaller. I don't know why I lost the 1. So okay, so that means that we're adding numbers. So then now we're adding num sub left. This is a little bit, I mean, now the invariant should still hold from, okay. So here we want to add this, and we just, what do we add from? A sorted list. Okay, and then now while right is less than R, we expand, we add, right? While left is less than L, then now we shrink. Oops. Okay, I might have done this in the wrong order actually, but maybe I think we move those in the wrong order. And then now the median is going to be, we still need a sum. We need to do like so many things, but the sum is easy, right? We just do a prefix sum. Right, because then now, did I just skip that part? I guess so, maybe. So the idea is that, okay, you have the median, everything bigger will go down. So it's not just a sum, right? We have to do a track on this. Do we have to track on this? I remember this part because this is the part that like in the one of the two contests I won, I had to do this part with a rolling median. It's not a prefix sum. I'm thinking of a different problem. But this is so annoying to do, unless people have code for it. Okay, so we have the median, and then now it's just about now figure out the median. How is this not a more point wide? I guess people know the answer to this one maybe. Some left 1 hour. I mean, I guess it is the way it is. Okay, well, we just have to track, which is hard. But actually, before that though, let's print it out real quick. Print SL, see if it's right. 01, okay, 14, 02, 147, 1 00 is not an input though. Did I do them in the wrong order? It's possible. I'm looking at the wrong thing. Oh, there is a 00. Sorry. Okay. So I was looking at the wrong thing. I was looking at the wrong. Okay. 1 and 2. Okay. 02 is not possible, so that's why. 00 is 1. We're Gucci. 2, 4. So we get the median very easily. And we want to round down, I suppose. Okay. So then now we just have to keep track of the deviation from median. That is annoying. How do I want to write it? When we add a number, what does that mean? And we could track the rolling median and then track the rolling thing to the median, but it's just such annoying maths. Am I doing this weirdly? Maybe. But I think this is the way to do it. So this gives me the median. I thought I could just do the sum and it becomes easy, but that's not true. No, I don't think there's it. If only we can get only the sum of the bigger numbers and the smaller numbers, but yeah, we have to keep, I mean, it's fine, we have to keep track, I guess. That is annoying, a lot more annoying. Yeah, I mean, we just have to do the 2 heap way, right? And then once we have to sum, it's not that bad, but I feel like people have this pre-written. Yeah, I'll write a class for it. I feel like I have this somewhere, honestly, but I don't know where it is. Just use sort of this. I could use heap, but is that worth it? Okay, so when we add a number, what happens? Let's say, okay, invariant is that and then the no, I mean, we can do this, but the idea is still trying to. No, I mean, I guess that's fine. I think all we need is track left sum. Okay, and we just kind of do it every step of the way, right? When we add here, right? So then now, yeah, okay. It is annoying, but it is fine, maybe. So then now, if self.left length of this is greater than self.right plus 2, then we re-index it. So then now the biggest number, right? Something like that, right? Add is easy, but subtracting, removing is hard, maybe. Okay, right, so then now if x is in self.left, then I guess maybe not. Maybe we should try to the duplicate case I'm trying to think through a little bit. No, let's just do it this way. We'll just normalize. Okay, so if right got too big, then we want to take the smallest number and we move it, right? Yeah, because then now, oops, then now they should be equal. Oh, actually, well, now they should be, left should be bigger than right plus 1, right? So the invariant is that right is equal to left plus 1. We could probably assert it actually. Okay, and then now if, well actually I guess this part we can just copy and paste. Maybe we even use a helper, but I think this is fine for now. Okay. All right. Okay, so then now the median should be a decorator, but or it should be a property, but okay. Yeah. But we don't care about the median actually. I mean we do, but we want the delta, right? So then we have the median, and then it is the sum on the left side, right? So then left minus median times the other way around, because median times length of self dot left. Yeah, whatever left dot. Nope. Right sum should be bigger. I mean it's, we probably just slap in slap a thing to it, but okay. So this should be actually still not correct because we didn't take account k, but that's easy. Is it delta? What do I call it? Delta, right? Okay. Okay. As we said, oh, the -2 actually is pretty bad. 3 is probably not bad, not good either, but that's okay. I thought I was just going to do this, but I mean this, no, okay, let's see what's going on here, right? But at least this should be a frame. I think we're mostly done. Ooh, I could submit by accident almost. Okay, so we have 0, 1, and let's we have 1 and 4. The median is 1. The delta is going to be 3. So yeah, so that seems good. Right. I could do some in my head for these numbers. Okay. Oh, the right delta. Did I mess up the signs? Well, the sorted list is just wrong. So it's okay. So there is some inconsistency here, which is fine. Did I mess something up? Clearly. So we add the 7. Oh, I don't rebalance. I'm dumb. I actually I make the same mistake a lot, so this is actually dumb. Okay, so we have to figure out. Let's just write rebalance. Maybe I have to double check that one actually. I think I make the. I don't know why I do the same thing with the heap. That's okay. We can fix this. Now we just don't do that, right? We want to write if x is That's then you go to sub that left the biggest number, then we just add it, right? Or maybe just the smallest number on the right side, because then we can just rebalance, right? Otherwise, then okay, so this okay, am I good enough to remove some print statements? I'm good enough to YOLO. I don't know if I'm good enough. Is it good enough to, you know, is it fast enough? I'm not even trying on a big thing, so maybe even timeout. But I mean, timeout I'm okay with, honestly. I think complexity wise this makes sense. But yeah, I mean, it may just be a Leetcode thing, right? So what it is what it is. I'm missing about 100. No, only 40. I don't know. Well, let's see. If it's only this case and it still fails, then maybe. But 4 seconds. What is n here? N is. I mean, the sorted list does make it slow for sure. We do a lot of random things here. There's no denying it, but at least we're correct. I'm trying to think whether I 4,000. That's not even that big, honestly. Let me do a thing real quick. Just to see if it would time out. If it times out, then maybe I have to re-look at my mouse. No, I mean, it's still pretty fast, right? Like, so maybe it is just one of those things. Well, maybe it's just slow on the queries, not this, so maybe that's why. So maybe we can do, how many queries do we have actually? So n doesn't matter as much, queries 3000, right? So maybe we do something like the same thing as before. If it times out, then we know that we have a queries issue. No, it's still the same time, so I think it's just Leetcode not being great. I don't know why this is so slow though, but am I missing something on the thing? Am I messing up on the? Right, let me see if I'm just gonna chat GPT to see if I can convert this to Java. Just to see if it's fast enough, because I mean, at least it's correct, which is what I was hoping for anyway. I mean, that's what I usually hope for, because there's no point in hoping for it to not be correct. But yes, wait. No. I don't know. I'm not that confident about this one actually, to be honest. I mean, I'm happy that I use most. Maybe I'm wrong. Maybe, I mean, because 4 seconds for one thing is a little bit long. Maybe this is not just, maybe this the rate I'm doing is not fast enough. I have to think about one more thing. It's certainly possible. Right, this looks fast, right? Is it right though? I don't know actually. I mean, if it's wrong, it's wrong. Maybe it like overflows or something. It's fine. Oh, this is so dumb. This is why I don't do contests anymore. Python just like, you know, Python gets no love. And I was stressing out a little bit about it. I mean, not that stressful because it's not, but. I mean, it's nice even on a fake thing to finish top 100, and is because Python Leetcode things are bad, but how do they do it? What's PST? I mean, I guess that's what I'm doing. Oh, I mean, basically, it's what I'm doing. Right? I don't know what PST stands for. I'm curious. Yeah, I mean, this is basic. Yeah, I mean, this is basically what we're doing. I mean, maybe there's some. I don't know if that's true, but nonetheless, it is very similar to what I'm doing. I mean, that's what I was trying to do, but then I got lazy. With the min and the max. Oh, that makes more sense actually with the min and the max. Oh wait, no, they did it with a segment tree. I thought they did it with bit. Instead bit is, I don't know. But it seems like my idea is basically what people are doing. Okay, that's just not readable, but okay. Sparse table. Oh, PST means persistent segment tree. I didn't use a segment tree, right? Okay. I mean, I didn't use a segment tree, so I was wrong in that. That's what they were using for the median, but they do have this query range, which I kind of thought about this using a segment tree, but I thought maybe there's a way to do it. But I don't know how to get the thing about it, so I guess maybe sum left. How do you get sum left? Maybe there's some counting thing. I don't know. I don't know. That seems weird. I mean, I'm using square root decomp, so it's hard to say that I'm not using some crazy thing. I guess that doesn't load because I'm not a real contestant. But yeah, I mean, I'm using RMQ and square root decomp, so it's hard to say that I'm not using high machinery. So who am I to say about segment trees? Am I done? I guess so. I mean, I wish Python was fast enough, but I mean, probably combine this, but I don't think that's the issue though. So I don't know. I mean, it wasn't even close. Right? I spent 4 minutes on it, so if you want to tick off 9 minutes, would even be better. Was that 41? So I would have been like, well, I mean, still tougher. Like if you want to pretend my Python solution worked, that would have been like 55th or so. Anyway, I don't know, whatever. That's all I have with this one. Let me know what you think. It doesn't seem like people did it with square root decomp like I did though. Actually, maybe this person did, I think. This kind of looks like what I'm doing. So maybe some people did it with square root decomp, but not with the majority. And definitely people in Python doesn't seem to have done it that way. That person just didn't seem to do it in any way. I mean, this is square root decomp, so why is mine so much slower? Oh, they used it with bit. Huh. I didn't know that you could use that with binary index tree. Maybe I have to do some reading. That sounds more like the intended solution. I mean, the idea is the same. We just have different data structures. Did I say different structures? Different data structures. I'm having a stroke. Yeah, different data structures. So I don't know. Anyway, I'm happy that I got it. I it's kind of funny because I feel like I said, I've only done most algorithms like twice before in my life. So this is the third. And you may ask me, because I'm curious myself, like how do you come up with it? I think, and maybe I'll talk about it a little bit more on the actual video. And this is kind of like a little bit of a retro. Let's do a full retro because I don't remember the other problems anymore. But the idea is just that, well, I knew I needed to get the median, and that's just from problem solving. I'm not going to go into that just because, you know, not meant to be a full thing. So once you get the median, and I did the rolling median thing, it's just because I was thinking about like, so the visualization that I was visualizing is that, okay, now with all these segments, I was trying to figure out how to do like a sliding window thing, honestly. Or not sliding window, a sweep line, sorry. A sweep line thing. And then in that visualization, I was like, well, no, if you do a sweep line, you have to move the right endpoint left and right as well, not just sweeping the left. And then in that visualization of moving the right endpoint left and right, I was like, oh wait, can we do square root decomp? And I just didn't even remember the name. I've done it only twice, and it's not something that I, well, I've only done it twice. So yeah, I don't know. But I had to search for the name because I don't know, I don't remember it. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, the problems, everything in between. Stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye-bye.